Hello everyone, today we're going to talk about element number 17 on the periodic table, chlorine. The previous video that we talked about was on argon. Argon is a noble gas. Unlike chlorine, chlorine is like the polar opposite of the previous element, argon, because unlike argon, chlorine is very reactive with its environment, just like fluorine. In the video that we discussed on fluorine, we talked about how reactive it is with almost all the elements on the periodic table. Chlorine being a halogen is no different. We're going to go over its properties, we're going to go over its history, we're going to go over where it's extracted, we're going to discuss the process that it takes to separate chlorine gas and where chlorine is acquired from in natural sources such as salt. Chlorine is involved in the dissolution of various types of substances, solids, and liquids. It's used in things such as hydrochloric acid, which is found in various things such as our digestive system and our stomach to digest the food that we eat. It's used in pools as a disinfecting agent to get rid of dangerous and harmful biological substances that may harm us while we're swimming in the pool. It's used to create various other compounds and various substances that we use every day, such as our credit cards, which consist of polyvinyl chloride, which is a combination of carbon, chlorine, and hydrogen. So let's begin. So chlorine is an essential chemical building block used to make many products. Here we have hydrochloric acid, which consists of hydrogen and chlorine. Chlorine is also used to clean water. Chlorine is also used to manufacture various food products, various plastics, polyvinyl chloride as previously mentioned, credit cards, and all the various things that polyvinyl chloride is used to make. Here we have a cube of salt, which consists of two elements, chlorine and sodium. Sodium salt binds to chlorine. Chlorine oxidizes the sodium and the sodium reduces the chlorine, and then they fuse to create a new ionic bond, which is structured in a cubic-like way, which at the macroscopic level manifests as those salt cubes that we know and love. Don't eat too much salt, because if you're consuming too much salt, you're consuming too much chlorine and too much sodium, which is not good for your body. In fact, the salt that we consume is used to produce the hydrochloric acid inside our bodies, inside our stomachs, to dissolve the foods that we eat. So that's one of the various reasons that we consume salt for. Chlorine chemistry is used to manufacture various things, such as these contact lenses. It's used to manufacture solar panels, bullet-resistant vests, energy-efficient windows, paint, and prosthetics. It's also used to create salt, sodium hydroxide, and hydrogen, which results as a byproduct of creating all of this. The two components involved in the molecule sodium chloride are sodium and chlorine. It's essentially a sodium metal oxidized by a chlorine halogen. The sodium gets oxidized by the chlorine, so it's a 1-to-1 ratio. Rock salt has been around in the form of halite for thousands of years. The main constituent of the salts discovered were in seawater. In fact, seawater consists of 3.5% salt in total, so 35 parts per thousand. If you were to extract a sample of seawater, you would find that around 3.5% of that total water that you extracted is pure salt, sodium chloride. Back then, Roman soldiers used to get paid in salaries, so that's why it's called a salary. In Spanish, the word for salt is sal, and the word for salary in Spanish is salario. They both have the prefix sal, which is even found in the English word for it, salt. Back then, the Roman soldiers were paid partially in salt, and that's where the word salary derives from in today's time. So when we get paid a salary, it all goes back to those Roman days where they used to get paid in salt. The Egyptians were able to extract salt from the ocean through evaporation. It just takes a little bit of time. You simply get the water from the ocean, you lay it out, you allow it to pool over and eventually evaporate to the point where only the salt, only the heavy minerals, and the things that aren't able to evaporate into the atmosphere are left behind. So that includes the oxidized metals such as the sodium chloride. The sodium chloride collects as a crystal. When the sodium chloride is dissolved, such as in the ocean, it presents itself in a different form. So here you can see that there is a water molecule involved. Water molecules are consistent of two atoms, hydrogen and oxygen. Since the oxygen is the oxidizer in the molecule, it's the one that attracts and binds to the electrons more heavily. In contrast, the hydrogen atoms aren't that attracted to the electrons. In fact, they're more passive about it. If the oxygen wants the electrons more, it's more than willing to give it to them. And as a result, the hydrogens build up a net positive charge at their ends. Here we see a positive charge, 2 positive charges which are representative of the hydrogen atoms, and 1 net negative charge which is representative of the oxygen atom in the H2O molecule. So as you can see here, normally the reason that water sticks to itself, the reason that water is both adhesive and cohesive, adhesive means that it sticks to other materials, and cohesive meaning that it sticks to itself. That's why in water, in cups, it stays stuck to the side of the cup, because it's both adhesive, sticking to the cup, and sticking to itself in the form of a water molecule, cohesive. When you drop sodium chloride, so you drop a couple granules of salt inside of the cup of water, you get a dissolution of the sodium chloride, which simply means that the positive sides of the water molecules are attracted to the negative sides of the chlorine, which is negative when it dissociates in the water, and the negative parts of the water molecule are attracted to the positive parts, the sodium of the sodium chloride part. So here we can see that this positive is connected to the negative. So the oxygen is binding to the sodium and the hydrogen is binding to the chlorine. Essentially what's happening here is that the hydrogen metal or the hydrogen gas is exchanging oxides. Previously being oxidized by oxygen, it's now oxidized by chlorine in the water. And the oxidizer oxygen is now oxidizing a new type of metal, sodium. The metals aren't really unoxidized, they just exchange what oxidizes them. So instead of the sodium being oxidized by the chlorine, it's oxidized by the oxygen now in the water. And instead of the chlorine oxidizing the sodium, the chlorine is now oxidizing the hydrogen in the water. So they just exchange what they're oxidizing as a net whole. As we previously reviewed, another term for salt is halite. That is the mineral term for salt. So again, quick review and overview. Halite, salt, sodium chloride dissolves in water. It dissociates because of the bonds and the ions and the polarity that it has. The Egyptians thousands of years ago obtained salt, the halite rock. They obtained it through evaporation of the ocean water, which consists of 3.5% or 35 parts per thousand in terms of quantity. And the Romans used to get paid in salt. That's where the word salary comes from. So whenever you hear my salary is, just remember that the word salary comes from the word salt. The Roman soldiers were paid salt back then, and that's where the connection to today's times comes from. So general overview of chlorine is that it's used in various types of chemistry. It's used to manufacture things that involve transportation, to advanced technology, to building and construction, to jet plane canopies, defense and law enforcement, and various other products that we use every day that we don't even realize involve chlorine chemistry. Although the final product may not include the element chlorine within the compound itself, chlorine is still involved in the process of creating that product. Various things in the advanced technology sector include tablets, phones, computers, HFCs, which are now banned because they dissolve the ozone layer away. Other things such as coolants, which are now replaced by safer alternatives that are used in the refrigerators. They're used in the manufacturing of chips. They're used in the manufacturing of components in cars. They're used in the manufacturing of paints. They're used to create windows that are energy efficient. Chlorine is needed to create Kevlar because Kevlar is a very complex and strong molecule that requires chlorine chemistry in order to generate it. Chlorine is used in defense and law enforcement in the aspect of night vision goggles. The process of using chlorine to create the final product is very crucial. Understanding how the chlorine chemistry affects all of these final products and creates them is essential for a society to be able to run, work, and function with all of these things that it requires. Apart from that, jet canopies such as in airplanes, because as previously mentioned, chlorine creates a lot of strong compounds. One of the strong compounds is jet plane canopies, which involve clear types of compounds that need to withstand high velocities and high speeds, because if they can't, they'll shatter, they'll break, and the person inside will be injured or killed catastrophically. Other things that chlorine is involved in is in transportation. It's involved in creating strong materials that are shatter resistant. It's involved in GPS, things that we use every day. Airplanes, the generation of boats, the creation of bumpers, cars, also trains that we use to transport everything that we use. So in quick summary, chlorine is used to generate, manufacture, and produce various types of compounds and products that we use on a daily basis. So chlorine is very important, although it's toxic in its rare form. It's used to create all of these things because of its potency and its reactivity with all of the elements, or most of the elements on the periodic table, similar to the way that fluorine reacts. So the modern history of chlorine, in which it's used as an isolated product, or it's used in a more specific way in which chlorine is applied and directed in forms that do not involve or do not directly involve sodium chloride or salt. The first usage and application of chlorine starts around 1648 with the German chemist John Rudolf Glauber. He obtained a strong acid in which he called the spirit of salt by heating most of the salt in a charcoal furnace and condensing the fumes in a receiver. So essentially what was happening is that he took basically salt, the salt that we use to season other things, and he mixed it with sulfuric acid. Sulfuric acid is a very energetic liquid that has the ability to rearrange and dissociate pre-existing bonds that exist in molecules. In this case, the sodium chloride bonds are dissociated by the sulfuric acid and they recombine. My theory is that hydrogen is a type of metal, considering that on the periodic table it's right below lithium and sodium and other elements that are resembling to metals. Hydrogen is simply a metal that gets oxidized just like lithium, sodium, potassium, and magnesium and other various metals on the periodic table. What happens here is that the sodium in the sodium chloride is oxidized by the chlorine, and the hydrogen in the sulfuric acid is oxidized by the oxygen and the sulfur. And what happens when they interact is that the oxidants exchange and the metals exchange. So the sodium and the hydrogen metals exchange oxides, as it says here. So the hydrogen exchanges its sulfur and oxygen oxide with sodium, which has a chlorine oxide, eventually resulting in hydrogen being oxidized with the chlorine that was previously oxidized with the sodium, and the sodium being oxidized with the sulfur and the oxygen that was previously oxidized with the hydrogen. So they end up exchanging and they end up becoming new molecules in the process. So what John Rudolph did here was mix sodium chloride, sulfuric acid to obtain hydrochloric acid and sodium sulfate. Hydrochloric acid is what is again used in our stomachs to digest the food. It's a product of mixing the salt and the sulfuric acid together. There's various processes and ways that one as a chemist or an individual can use to obtain hydrochloric acid liquid, but this is just one of the various molecular formulas and one of the various experiments that were attempted by other individual scientists. They weren't trying to directly obtain chlorine, but chlorine is involved in this process. It's the first time that chlorine was as close to as isolated as possible because it was bonded to a lighter and less visible metal that allows chlorine to be more present in the liquid here. Hydrochloric acid is very reactive because it's essentially almost pure chlorine. So moving on from John in Germany, we're going to move on into the future with Carl William Scheele. We talked about him in previous videos about the elements involving gases. He is very involved in the discovery of various gases on the periodic table, so he was a very popular scientist at the time. He was also involved in the element chlorine. He didn't discover it, unfortunately, but he did work with it, and he didn't even know that it was a new element that was yet to be labeled. That will come later. But what he did was important because he worked with another reaction that involved manganese dioxide or manganese oxide, and he, as previously mentioned with the hydrochloric acid, he mixed it with hydrochloric acid to obtain pure chlorine gas, magnesium chloride, and water. So as you can see, it's very important that previous people before us perform certain experiments in order to obtain certain compounds and certain things, certain products. That way the people that come afterwards are able to work on the work that was left previously by the other people, and they could build on top of that. And by building on top of that, they're able to continue and not have to reset. So again, Carl William Scheele was able to take on the hydrochloric acid that was already created and was already toyed around with and played with in the lab. Previously, it was not even called hydrochloric acid. It was called spirit of salt. Spirit of salt because it wasn't identified before. They didn't know what it was. They just knew that it came off of the salt itself. So the hydrochloric acid or the spirit of salt was used to interact with the oxidized manganese. Again, the theory that hydrogen is just a metal and exchanges oxides because it's oxidized by the chlorine is performed here. The hydrogen exchanges its chlorine oxide with the manganese, and eventually the product is that the hydrogen completely dissociates away from the chlorine. The chlorine self-oxidizes, which means that it forms a diatomic molecule, which means that it just bonds to itself. Things that oxidize can also self-oxidize. That means they can bond to themselves and oxidize themselves if there's no other elements present to oxidize them. So that's what chlorine does. Since chlorine dissociates from the hydrogen metallic bond that it's oxidizing, it just oxidizes itself. The manganese gets oxidized by the chlorine and the hydrogen gets oxidized by the oxygen with its previous bond with manganese. Summary: manganese loses its oxide oxygen and replaces it with chlorine, becoming manganese chloride. The hydrogen also loses its oxide chlorine and replaces it with oxygen becoming water, previously being hydrochloric acid. The hydrogen in the hydrochloric acid compound becomes also part of the water molecule, which gets created. The chlorine gas is then released from the hydrochloric acid and becomes chlorine, which is a diatomic molecule, self-oxidizing itself. The oxygen also involves itself in the water molecule, which becomes water. As a result, the chlorine gas is released afterwards, being reduced in the process. Carl William Scheele in 1774, the Swedish chemist, treated powdered black oxide of manganese with hydrochloric acid and obtained a greenish gas, which unfortunately he failed to recognize it as an element. That will come later, that will come now. The person who finally was able to identify, label, and recognize that chlorine was a new element and not just another compound in the lab was Humphrey Davy. We also talked about him before. He named chlorine from the Greek word chloros, meaning yellowish green, because it does give a yellowish green tint when placed upon a white background. He provided an explanation for its bleaching action and all the various properties that it possessed, and that's why he gets the credit for chlorine. So we can't talk about chlorine without pools, because as we know, there is much association with the element chlorine and pools in our early childhood and our late seniorhood, because as we know, every single person eventually interacts with the pool. We swim to keep healthy and we swim to have fun. Chlorine is always involved in the disinfectant process. If we ever run out of antibiotics, chlorine will always be there for us. Actually, the halogens, which chlorine belongs to, will always be there for us in case of antibiotic resistance in bacteria. Because of that, we use the element chlorine for its disinfectant properties in pools. And here we can see a pool has chlorine, because as individuals swim in the pool, they may secrete bacteria or viruses that they may contain within their human body. They may be sick, or they may have remnants of those viruses or bacteria when they were sick, and that can transmit into the water. Water, being a fluid, is conducive to the life of those viruses and bacteria and can easily transmit into another individual, being that we mostly consist of hydrogen and oxygen, being water, and that's why it's important to have a substance within the water that eliminates that bacteria and that virus transmission and prevents other people from getting sick when they're swimming in the pool. Because if, for example, let's simulate a world without chlorine in the pool, that would be catastrophic eventually, because the water would get dirty quickly, the people swimming in the pool would get sick. If you're swimming with someone that's sick, they would quickly transmit that disease to you. If they have diarrhea, that diarrhea would easily transmit into the water, and all those diseases would transmit into the water. And if you are one of those individuals that tends to inhale water or tends to accidentally breathe in water from the pool, you would unfortunately inhale all those viruses and bacteria from the diarrhea water, and you would not have a pleasant experience in the near future. And that's why it's important that we have the element chlorine in the water. As a result of having chlorine in the water, you get that nostalgic pool smell. The nostalgic pool smell creates things known as chloramines. So chloramines are pronounced chloramines. So chloramines right here. Chloramines are produced when ammonia and chlorine combine to produce various types of molecules. One of them is a chloramine molecule, which consists of nitrogen, hydrogen, and chlorine. The reason that nitrogen and hydrogen come into the picture to combine with chlorine is because the ammonia combines with the chlorine, and the ammonia comes from the urea from our pee. When it decomposes from ammonium, it decomposes into ammonia, and that eventually goes into the water, and in the water it combines with the chlorine, and then it produces a new compound or new types of molecules known as chloramines. And chloramines can come in different forms, such as monochloramine, which is NH2Cl, or dichloramine, which is NHCl2, or nitrogen trichloride, which is NCl3. All of these molecules are presented here, and as this diagram says, ammonia and ammonia-like compounds found in human sweat and urine react with hypochlorous acid, producing chloramine. It is these, not chlorine, that cause the characteristic smell of swimming pools. They can cause wheeziness and sore eyes for some swimmers. So this is resembling to chloroform, which is produced by combining chlorine with another compound resembling these substances presented here. Do not misuse the information presented here. This is for educational purposes. Chlorine is a very dangerous compound, only to be handled by the most responsible of individuals. So be be very cautious, be very wary of the situations that you put yourself and others into when it comes to these compounds. They're halogens. Again, they're very reactive. If you understand chemistry, then you understand that these compounds are not to be trifled with. So be very careful, be very wary, be responsible. That's not stating the obvious for some people. Unfortunately, it has to be stated because, again, chlorine is not a compound that you just want to mess with, especially if you're isolating or separating it. Chlorine is not exclusively in swimming pools as a disinfectant. In fact, it has to be presented into the swimming pool, into the water as a compound. So here we have the two compounds that are usually used to introduce the chlorine into the water. Sodium hypochlorite, which is a combination of sodium, chlorine, and oxygen. And calcium hypochlorite, which is a combination of calcium, chlorine, and oxygen. So these two molecules are used to introduce chlorine into the water. They dissolve, and then that causes the chlorine ions to dissolve into the water, and luckily they still do their job and they disinfect the water accordingly. So again, a quick review. Chlorine is a big component of swimming pools. Chlorine is used to filter and clean the viruses and bacteria that may exist in the water due to various factors that may occur that introduce those things in the water. Chlorine is a necessary additive to the water in order to maintain conditions at a reasonable level where people are not affected so much by the chlorine but are still able to enjoy relatively clean water. So that was Chlorine Explained in 25 minutes or less. If you're interested in watching the previous video, it was on argon explained in 14 minutes or less. Unlike argon, chlorine is very reactive with just the removal of one proton and one electron. It's incredible just how reactive and how many compounds more the atom or element can form. And argon, being a noble gas, does not combine with anything. Chlorine, on the other hand, combines with various elements on the periodic table and oxidizes various metals. Chlorine, reactive. Argon, not very reactive. If you're interested in watching a contrast to chlorine, click on the link in the description below. It's on argon. It'll take you right to it. Make sure to like, comment, and subscribe if you guys enjoyed the video and if you found it helpful. Have a good day.